Hi, my name is Jinhee Chang, and this is my Lab 5 Magnetic Braking with Faraday. And so the introduction is the purpose of this lab is to study the interaction between two falling magnet and tube of aluminum foil, which produces an interesting result, something that we're going to be seeing in this lab. And in order to do so, we will collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet tube interaction computationally, and then compare the computational predictions with the observed data. And so some key concepts is Faraday's law, which is pictured on the top right, Biot-Savart's law, which is in the middle there, Newton's second and third law, which is F equals ma, and for every reaction there will be an opposite and equal reaction, and then Ohm's law, which is pictured on the bottom right. And then so some assumptions that I made was the magnet used to model the magnetic dipole, and the aluminum foil modeled the tube that it falls through, and that air resistance doesn't matter, and gravity and magnetic force from the aluminum tube are the only forces on the magnet. So the experiment is we mark the north pole of the magnet, and then we use the app to determine which end is the north end, and then we hold the tube vertically and position the magnet just above the top opening and hold the phone with the other hand and get the entire length of the tube in frame on smartphone camera. And then what we're going to do next is record the video on the phone and drop the magnet through the tube, and then scrub through the video in Video Player to find the time code when the magnet enters the tube, and then the time code when the magnet exits the tube. And then between that, we're going to calculate the time it took the magnet to fall through the length of the tube, and then we find the average time it takes for the magnet to fall through the tube. And so some checkpoint questions is based off of the PDF file for the lab instructions, and it's why can't we use a ferrous tube like a steel pipe? And the answer to that is because it interferes with the magnet, and then what happens to the magnet and how does this compare to the magnet falling in free space without a tube? And so the answer to that is that it's slower than it does in free space because of magnetic force, because if gravitational force goes down, then the magnetic force should be pointing up due to Newton's third law, and so the magnet is falling slower than it would versus if there was no tube there. And so the measurements and data, we have the length being 0.3 meters, width being 0.005 meters, the inner radius being 0.025, and so on and so forth. And the average time that I got was 1.22 seconds. And then this is a glow script code. This is the beginning. And then step 1, I filled out based off of what the results that I just shared previously. And then the mu mag is actually from one of the previous labs, lab 3, and that was the value that I got for the magnitude of the magnetic dipole moment. And then so on and so forth. And then we create a function to calculate the magnetic field of the bar magnet, and then we have also our initial conditions. And then what we did next was we created a function to calculate magnetic flux, which is pictured there. And then we did a simulation loop, and then we did the magnetic force from the tube of the magnet, and so on and so forth, including the coloring of the ring. And then we calculated the magnetic force on the magnet, and then we edited the next one line. And we plotted the graph, and then this is what I ended up getting. And so what you see in the picture on the top left is the blue part is actually the north pole, and the red part being the south pole in the magnet, so to speak. And this was the graph that I got. So I think it was at first I was really shocked by, I guess, the shape of the graph, but overall I think it makes sense. And then the tube was created, and then the time that it takes to go through the tube is 1.089 seconds, which is kind of pretty close to what I got, but also a little bit far away from that. And so to discuss, I guess, some sources of error is human error. It's hard to see stuff on my phone personally for me, and so maybe I could have gotten the timestamps wrong, because I tend to overestimate my timestamps. And then the possible source of error from lab 3 could be carried forward, like we had a wrong magnetic dipole magnitude, and then we carried that value forward, and that would have not been very good. And then so some ending question is, what if the resistivity of the conductor were conducted as close as possible to 0, and how the dynamics of the falling magnet change? So for Ohm's law, the induced current would be a lot greater because resistivity is lower, and so there would be a greater magnetic force, and that prevents the magnet from falling, which could maybe prevent falling not as fast, or it could potentially prevent falling altogether. And so what if holes or slots were cut into the tube, and how would this affect the ring currents in your model? So the induced currents would be less because of the fact that there were holes cut, and the magnet would fall quicker because of less magnetic force. And that's it.